Welcome to the first video lecture for Chapter 5. Here we'll be covering circular motion. It's one of my favorite topics because there's so many applications as we go forward. All right, here we go. First lecture. Acceleration is the rate at which velocity changes. So therefore, an object can be speeding up, slowing down, or, since it's a velocity, changing direction in order to be accelerating. We define uniform circular motion as anything that's traveling in a circular path at a constant speed. We use speed and not velocity here because the direction will be changing as it moves in this circular path. The period refers to the time it takes to complete one revolution, or one cycle. We'll see this term again, period, when we look at simple harmonic motion. Once again, the velocity is always changing direction for something traveling in a circular motion. Here we have a little animation that shows the velocity vector and how it changes as it moves around a circle. Speed is equal to distance divided by time, or the rate the distance is covered. The distance that it takes to go around a circular path is equal to the circumference, 2 pi r. The time is equal to the period, the length for one revolution. These come together in our simple little formula here for speed. Ta-da! Centripetal is merely a word that refers to any acceleration or force that is center-seeking, anything that is seeking towards the center. Here we have the equation for the centripetal acceleration. It says that the centripetal acceleration is equal to the speed squared divided by the radius of the circle. The magnitude of the acceleration is always directed inward towards the center of the circle. This will be applied more when we talk about centripetal force. If you want to see the derivation, please look in your book. It uses similar triangles for the calculation of the centripetal acceleration. Here we have two little bugs sitting on a turntable. What this animation will show is the direction of the vector for the velocity in green and the acceleration in red. So as we add some rotational speed, here we have the velocity is getting bigger. Notice the acceleration is directed inward. The velocity remains perpendicular to the acceleration at all points. The velocity is also tangential to the edge of the circle. Notice that the acceleration for the outward bug is much larger than the bug that is closer in. Yes, Stacy? Here's a review question for the previous lecture. A race car completes a quarter of a lap. That's only 1/4 of a lap around a circular track that has a radius of 850 meters. It takes 9.2 seconds to complete this quarter of a lap. I would like for you to answer, please. What is the distance covered during one lap? What is the race car's speed? What is the acceleration of the race car? Assuming the speed that you found in question number 2, how long would it take the race car to drive 25 kilometers? Please actually take these questions. You can do the work wherever you wish in your notebook or on any other sheet of paper, but please answer them on the website below the videos. There should be 4 questions right there that are similar to these, and there should be a place to input them right there. Please do that, and have a good night. Thank you very much.